Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work for this particular problem. We want to determine the stiffness of the spring K. Uh, okay. Uh, to solve this problem, we will we'll consider the determine the potential function. Okay. Uh, Considering also the spring force and the force of the members due to the weight of the members A, B, and B, C. Okay. And differentiate the potential function with respect to theta and solve for k. Of course, theta is given to us as a 30 degree. So the weight of this one we act that way. So let's call it W. Okay. And the weight of this one will also act this way. So the weights are equal. Let's just call them this W as well. All right. This is theta given. All right, and the length AB, the lengths are given. All right, so we can just determine for the bars AB and AC. Now for one of them we are going to have the y. Okay, but before that, let us fix our we're going to have the spring force coming this way. Let's call it F subscript S, and this way also subscript S. All right. Okay, and we're having the displacement here due to this one. Let's call it S over 2. And for this other force, let's call the displacement S over 2. Sorry, S over 2. Okay, so that if we consider the bars now, A, B, and BC, for one of them, we are going to have the vertical distance. Okay, is going to give us a Y. And of course, remember that it will act, the weight will act through the center of gravity, half AB, so that half BC. So it's going to give us equal to 1 over 2 uh, times 2. The length of AB is 2, the length of BC is 2. They are equal to sine theta. Okay, so having that for one bar, therefore for the 2 is going to give us, when we add them, we'll get for 2. All right, so the potential, the gravitational potential, let's call this B sub with G, is going to give us, it's actually going to be, uh, let's call it weight times Y. Sorry, yes, weight times Y. All right. So if we do that, leave that there, we can consider also the spring. For the spring, we are going to have S, considering the first spring, okay, we're going to have it to be 2 cos, sorry, consider the first force rather, F sub with S to the side of A. Okay, we're going to have it to be 2 cos theta. Okay, displacement, and let's call the other one S2 is going to be 2 cos theta. All right. Therefore, for the extension is going to give us for one, we are going to divide that by 2, and for that, which is S over 2. Okay, it's going to be S over 2. Okay, calling the full displacement for both S and 1S. So if we divide it by 2, we are going to have it to be, for 1 to be 2 cos, okay, theta, 2 cos theta minus 0.5, okay, minus 0.5 instead of minus 1 meter, because the in original unstretched length for the spring is 1 meter. So for half, it's going to be minus 0.5. All right. So we have that now. So we can now go look at for the uh, we know that for the elastic potential energy, you're going to have this V sub E is going to give us that spring force, okay, so S times S over 2, which is the same thing as saying is K, the spring constant, the S square over 2. All right. So considering uh, we are talking about F subject S, uh, two of them. Okay. So we're going to have this. If you separate it divided by 2, we will have this is also equal to this plus K, all right, into S over 2, all right. So we have that, all right. So we can just plug these, okay. So for our potential function, is Vg is of G plus V is of E. So it's going to give us equal to minus, of course, just plug in values into it. We're given, so if we do that, we're going to have for the first, for the first 8IB, for remember AB, is going to give us minus into minus 8, okay, sine theta, okay, minus, consider the second one also, into minus 8 sine theta, okay, the other member, that's BC, okay, so we'll have that. Then consider the spring, the first one of the F sub with S, the first one, we're going to have it to be K over 2, okay. Remember we got this earlier on, is the half of the displacement is 2, okay, 2 cos theta minus 0.5, okay. Then of course remember that it is squared, the displacement there, you square it, then you also plus, consider the other F so with S, we have this other spring force, same thing as 2 cos theta, minus 0.5, okay, squared. Now if you sub this out, you are going to arrive at uh 16, okay, 16 cos theta, sorry, 16 sine theta, 16 sine theta, okay, plus K over 2, K over 2 into 2 cos theta, all right, minus 0.5 minus 0.5 squared plus K over 2 into 2 cos theta minus 0.5 squared, all right. So we can just differentiate this for the to get the equilibrium position. Okay, for the equilibrium position, the relation is the v, the theta, of course, should be equal to 0. You sub that, you're going to have it to be equal to 16 cos theta, cos theta, okay, plus 2 over 2, 2 over, all right. So just, okay, plus 2 over 2, okay, minus 16. So let's just solve everything out at once. So the 16 cos theta minus, sorry, 16 cos theta, okay, minus 16 sin theta, 16 sin theta, okay, all right, cos theta, sin theta, cos theta, okay, k, right, plus 4 sin theta, 4 sin theta k, sin theta k equal to 0. Remember that we should equate it to 0. So if we do that, we can just solve for k. Remember that theta is given to us as 30 degrees. If we do that, plug in that, we are going to find k, making k the subject of the formula. K is going to give us 2.8 IB. Remember to plug in theta as 30 degree, IB per feet. So this is the spring stiffness, okay? That's the magnitude of the spring stiffness.